mga kanasyon, andito na naman po si Angelito Celestial, ang batang walang pera.
Today we're going to be doing a tutorial video, but before that, let me ask you one question. If you're a practicing civil engineer, have you ever had the chance to design any underground water tank structure or any underground retaining structure like basement? If so, what software have you been using? Is it SAP? STAD? You can comment down below all those software that you're familiar with, their advantages and disadvantages perhaps. But for today's tutorials, we are going to apply soil and water pressure, or we called it the varying distributed triangular load, using the special feature of Etabs, which is the application of shell loads non-uniform. Are you guys ready for this tutorial? So here we go.
Hello guys, I'm introducing to you a water tank with a length of 20 meters and the width of 3.7 meters. As you notice, it is divided into two compartments, 10 meters each. Now to have a better understanding of this water tank, let's get inside cross-section 1. As you observe, the initial thickness of the wall is 300 mm, but that's not the final size yet. Our final size will come from our analysis using Etabs and other parameters like crack width. Also, the height of the water is restricted to 3 meters with a minimum air gap of 300 mm. But if you try to look at my pressure or water pressure diagram, it's different. Here is 3 meters, but on my pressure diagram is 3.6 meters. Why is that so? Because I assume to be on the safe side, and at the same time to unify my solution, I assume a total height of 3.6 meters. Now if you want to do a exact solution or computation, it's up to you, but on my part, I just want to be simplified, and at the same time we're not just dealing with water but also earth pressure that is acting on the opposite side with a height of 3.6 meters. At service, we have two main forces that are acting on the wall. One is the water, and second is the presence of the earth or the earth pressure, plus if there is a surcharge load on top of it, you may add on your solution. But I would like to introduce to you two cases or scenarios where the water tank wall may be subjected at critical point. The first case is just after the construction, meaning to say there is no backfill yet, because we're gonna test for the water leak. So there is no any soil on the perimeter or backfill on the perimeter of the water tank. Only water is available. So as you can see on my pressure diagram, it's only water. The second case is during maintenance, meaning to say the water tank is somehow being emptied. So without the presence of water, only the earth pressure plus the surcharge load is going to be assumed. Now for this problem, I have assumed a surcharge load of 12 kilopascal. You may find it too much, but for the purpose of computation, I have assumed 12 kilopascal. I would like also to highlight some important points here. The water table is just at the base of the water. Also, the angle of internal friction is 30 degrees, and the density of the soil is 18 kilonewton per cubic meter. Now, where are these data coming from? It will come from the soil report. Now at this point, I want you to focus on these two diagrams here, because later on we're going to be computing for the maximum pressure at the base for these two diagrams. For the first diagram, of course, it's a water pressure. It is represented by a triangular load or a uniformly increasing load. Again, for this case, only water is going to be considered for the analysis. For the second diagram, as you notice, it is represented by two shapes. One is triangular and the second one is rectangular. For the triangular load, that represents the earth pressure, while for the rectangular load, that represents the surcharge load. Again, for this case, only earth pressure and surcharge loads are going to be considered for the analysis. Now the question is, how are we going to compute for the maximum pressure at the base for both cases? So first, let's compute for the maximum pressure at the base of the first diagram. Of course, our formula is P equals gamma water, height of water. I hope you can still recall this formula from your hydraulics. Now, for the gamma water, of course, that's 9.81 kilonewton per cubic meter times the height is also given as 3.6 meter. Let's use our calculator. 9.81 times 3.6 equals, that's how much? 35.32 kilonewtons. We will write here 35.32 kilo Pascal. This one will cancel out. So what remains is kilonewton per square meter, or 35.32 kilopascal. So this is the pressure at the base of, the first case, which is 35.32 kilopascal. For the second case, it's quite a bit tricky because we're going to be introducing a coefficient, which is the Rankine's coefficient, to solve for the pressure at the base given the soil pressure and the surcharge load. So we're going to be dealing first with the triangular load. The triangular load represents the soil pressure. It is given by the formula. Let us assume that this is P1 and this is P2. For P1, it is given by the formula. It's still the same as water pressure, gamma of soil times height of soil. Okay, but we have to multiply a coefficient here called Ka. What is Ka all about? This is a Rankine's coefficient for active pressure. And it is given by the formula 1 minus sine of the angle theta divided by 1 plus the sine of the angle theta. As we all know, the density or the angle of internal friction is 30 degrees, which means that we're going to be substituting it here, 1 less sine 30 degrees. All over by 1 plus sine 30 degrees. Now, using your calculator again, 1 less sine of 30 degrees divided by 1 plus sine of 30 degrees. That's a total of, that gives 1/3. 1/3. Meaning to say that P1 now is equals to 1/3 of the density of soil. Density of soil is already given, correct? It's 18 kilonewton per cubic meter. It's here, 18 kilonewton per cubic meter. So we're gonna substitute from the formula 18 kilonewton per cubic meter multiplied by the height of the soil, which is 3.6 meter. Let's use our calculator. So it's 1/3 times 18 kilonewton times 3.6 meter. That's a total of 21.6. So this is 21.6 kilopascal. That's only for P1. What about P2? For P2, it is given by the formula KO multiplied by QA. Now, what does this KO all about? KO is a Rankine's coefficient for a condition where it is at rest. Meaning to say, like, for example, for surcharge load, it is at rest. So we're going to be using KO. And QA represents the surcharge load. So direct substitution, KO is, we don't know yet the value of KO, but we can compute. KO is represented by the formula 1 less sine of theta. 1 less sine of 30 degrees. Let's use our calculator. 1 less sine of 30 degrees equals 1/2. So it's 1/2. 1/2. P2 equals KO 1/2 of 12 kilopascal. That's a total of 6 kilopascal. Now, that's just P2. What we are after is the total pressure at the base, which is the sum of P1 and P2. P now equals P1, which is 21.6 kilopascal. Don't forget the units, plus 6 kilopascal, which is the P2. That's a total of, using our calculator, where is it? So that's 21.6 plus 6 equals 27.6. Where's the pen? 27.6 kilopascal. So did you notice if we try to compare pressure 1 and pressure 2, for the first case, you might guess that this is smaller because it's only represented by one shape, which is triangular, while for the second case, it is represented by two shapes, which is triangular and rectangular. You might guess that this is bigger as compared for the first case, but as you can see, the pressure at the base for the second case is 27.6 as compared with the first case of 35.32. So that's all for the pressure at the base of these two diagrams. Now, we are going to consider these pressures in our models using the Etabs. Finally, we're gonna be creating our Etabs model. We are now at the start page of Etabs 2016. This white background here is the working area, and on top of it are the different menus. They are arranged according to when you're gonna use them, or seemingly like in a chronological order. On the second level are the different shortcut icons. These icons will help you to save time in creating your model and at the same time doing your analysis and design. On the left side of the working area are the different toolbars to create and edit your model. So instead of getting inside these different menus, you can directly use these tools to create and edit your model. So let's get started. To start with, click File, New Model, and it will give you three options to initialize your model. The first option is Use Saved User Default Settings. If you haven't saved user default settings yet using command options, then Etabs will give you default settings. The second option is Use Settings from a model file. This will copy the setting of your old or previous files. But for the sake of this tutorial, I would like you to choose Use Built-in Settings with where you're gonna choose your display units. Since we are more familiar with the metric SI, so keep it metric SI. We're not gonna use still section database and still design code, so keep it as default. And yes, you have to choose the latest concrete design code, which is ACI 318-14. If you're done, then click OK. And this new model quick templates will pop up on your screen. Now before we continue, for the sake of the beginners, there are many options to easily create your model. One of the best options is to import architectural plan and grid lines, so you will not be creating all of this here manually. But since we are dealing with a very simple structure, which is a water tank, we're gonna use this quick model template to create our grid lines and story levels. Etabs will give you uniform grid spacing and simple story data as default, but we need to choose custom grid spacing and custom story data to specify our grid lines and to specify our story data. First, we have to edit story data, and this screen will pop up, which you need to specify your story levels as well as your heights and elevations. But we only need one story level. So hit your control button and select all these three levels above, right click, delete story, delete existing structure at story, and right now you only have one story level. Let us say that the top of the water tank is called the ground level with a height of 3.6. I hope you still remember the height. If you're done, click OK. Next, we need to edit grid line data. And for this, I would like you to click Edit Grid Data, which will give you grid system data. Keep G1 as it is, but click Display Grid Data as spacing, which is much more easier than specifying ordinates. Let's go back to our plan. We can specify 3 grids at X with spacing of 10 meters. And also we can specify 2 grids at Y with spacing of 3.7 meters. Keep in mind those numbers and let's input it here. We only need 3 grids at X, so we get rid of D and specify our spacing as 10 meters. If we're done with X, let's go to Y grid data. We only need 2 grids at Y, so we get rid of 3 and 4 and specify our spacing as 3.7 meters. If we are done, click OK and make sure that grid only is selected. Click OK and Etabs will give you 2 default windows. one 3D view, and one plan view. But for easy modeling, let's close 3D view for the meantime, and let's focus on our plan view. But before we continue, it is important to save our file first. To have a copy, let us name it as water tank, just in case something wrong is gonna happen. Next, we are going to define our material properties. And for this, click Define, Material Properties, and it will give you these default values for materials. Since we are updating the concrete compressive strength, we choose 4000 psi and modify it instead. For this project, we are going to use 30 megapascal compressive strength of concrete. So I changed the name to C30. It depends on you how you will name your material. To change the strength of the concrete, go to Modify Show Material Property Design Data and change the strength of the concrete, which is 30 megapascal compressive strength. If you're done, click OK. But don't forget to update the modulus of elasticity. For the modulus of elasticity, we are given the equation: the weight of concrete, which is 2,400, raised to a constant value of 1.5 times another constant of value of 0.043 multiplied by the square root of the compressive strength of concrete, which will give 27,692. Input that value here, 27,692, and if you're done, click OK and save the material. Now it's time to define the section properties. We will define sections for wall and slab because these are the only elements we're going to be using for this project. Click Define, Section Properties, go to Slab section and choose Slab 1 and then modify the property. Now, for the slab covering the water tank, we are going to assume a thickness of 200 mm solid slab. So I call this as 200. So it depends on you how you will name your property. And don't forget to update the slab material. We're going to use 30 megapascal compressive strength of concrete. Also, for the modeling type, we will assume an in-plane stiffness only. So we will choose membrane type. And of course, don't forget to update your modifier. For slab, we will apply 0.25 for bending. These values are from ACI code. When you're done, click OK. And of course, very important, you have to update the thickness to 200 mm. Since it's already 200, so we don't need to change it anymore. If you're done, click OK and save the property. Next, we're going to define the material properties for wall. Click Define, Section Properties, and go to Wall Sections. Modify Wall 1. Since we assume that the initial thickness of the wall is 300, I call this as W300. So it depends on you how you will name your property. Don't forget to update the wall material to C30. Since we are assuming that the wall will undergo in-plane and out-of-plane stiffness, we will put here shell thin. And of course, don't forget to update the modifiers. Both bending and membrane will be 0.70. Where did I get these values? It's all from the ACI code. You just have to go and read it. When you're done, click OK. Very important, you have to update the thickness to 300 mm. Click OK and save the property. Finally, we are now going to model the elements. First, we will start with wall. By making use of this toolbar here at the left side of your screen, Draw Walls, it will give you the properties of the object. Choose the right property, which is W300, and start modeling your walls. As you can see, I'm doing it in a counterclockwise manner. You have to be consistent with your directions so that you will find no problem for the interpretation of the results. When you're done modeling your walls, next is the slab. It will give you the property of the object. Choose the right property, which is S200. And same goes with the slab. You have to do it in a counterclockwise manner. Now that I'm done modeling my walls and my slab, the next thing that I'm gonna do is to apply supports. Go to the base, apply, okay, and select the points. You have to assign restraints. Since it's a footing or a mat foundation, then you have to choose fixed support. Click OK. When you're done, set your model in a 3D view by making use of the 3D button here. The next thing that we're gonna do is we need to apply mesh for both walls and slab. Let's choose walls. Click Assign, Shell, and Wall Auto Mesh options. Here you're given wall meshing options. Choose Auto Rectangular Mesh and make sure to go for Advanced. Select an approximate maximum mesh size of 1.0 meter. Click OK and save. Next, we're gonna apply mesh for slab. Select slab, go for Assign, Shell, and Floor Auto Mesh options. Here, you will select Auto Cookies Cut object into structural elements to be compatible with the walls. Make further mesh options to 1 meter. If you're done, click OK. Now, if you want to have a look of the shell analysis mesh, you can go to Set Display Options and click Shell Analysis Mesh. Click OK. Next, we will assign the load patterns. Go to Define, Load Patterns. For this, we will call EH for soil and WH for water. Let's have first WH. Since the type of load is not fixed, it is then considered as live load. Then click Add New Load. Next is EH. We will also consider the type of load as live load. Then click Add New Load. Now that we already defined the load pattern for soil and water, you may click OK. We will now assign the loads. But first, I would like you to have a view of what a non-uniform loads look like. Click Assign, Shell Loads, and Non-Uniform. As you notice, the non-uniform load P is expressed by the equation AX plus BY plus CZ plus D, where X, Y, and Z are the global coordinate system. Now, to have a better understanding on how to supply this A, B, C, D constant here, let us go back to our pressure diagram. Again, let us recall the general equation of non-uniform pressure in Etabs. It is given by the equation P equals AX plus BY plus CZ plus D. But this equation can be simplified further. If you recall, the global axis in Etabs, this is the vertical axis, which is the Z-axis, the horizontal axis X and Y. Now, if you look at the pressure diagram, the force is only acting at the vertical axis, meaning to say that the component at X and Y is 0. Eventually, this will cancel out. So the equation boiled down to P equals CZ plus D. With this equation, we now know that the pressure diagram is a function of the height. Now let me just discuss important points here before we continue with defining the values of C and D. For the first diagram, at Z equals 0, the pressure is 35.32. But as we go to a height of 3.6, the pressure will eventually reach to 0. For the second diagram, at Z equals 0, or at the datum, the pressure is 27.6. But as we go on top of the water tank, the pressure will become 6 kilopascal. Now, having known all those points, we will now apply to the general equation. First condition, using the first diagram, at Z equals 0, as I have said, the pressure is also 35.32, meaning to say, supplying those points here on the general equation, we now have 35.32 equals C multiplied by, of course, our Z here is 0 because we are at the datum, plus D. This will cancel out, meaning to say that our D is 35.32. Case 2. At Z equals 3.6 or at the top of the water tank. P, the pressure will eventually reach to 0. So 0 equals C multiplied by the height of 3.6 plus D, but we already have the value of D, which is 35.32 plus 35.32. Simplifying the equation, we now get the value of C as negative 35.32 all over by 3.6, which is negative 9.81. For the first diagram, we now have the value for C, which is negative 9.81, and D, which is 35.32. We now go for the second diagram. At Z equals 0, we know that the pressure there is 27.6 kilopascal. Substituting to our general equation here, we have 27.6 equals C multiplied by 0 plus D. So we have now the value of D, since this will cancel out, as 27.6. Second condition will be at Z equals 3.6, or simply at the top of water tank. Our general equation will be P equals Cz plus D. Our pressure there is not 0, but we have 6 kilopascal. 6 kilopascal equals C multiplied by the height of 3.6 plus the value of V, which is already computed as 27.6. Now simplifying further the equation, C now is equals to, using your calculator, C now is equals to negative 6. Now we already computed the value of C, which is negative 6, and D, which is 27.6. We now have the values of C and D for both cases. Next is, we will apply these values in our Etabs model. Now we are ready to apply the loads, but before that, let me create the load combination. Click Define and go to Load Combination. Add New Combo, and let's create EH Service. Click the load name and select EH. Now I'd like to discuss some important points here. Since the two forces are acting towards each other, meaning to say that the soil is pushing the wall inward while the water is pushing the wall outward. So to be consistent with the local axis, we will assign a scale factor of -1 for EH. And click OK. Now we add another combination, which is WH Service. And we choose the load name as WH. We will assign scale factor of 1 and click OK. Now we're going to create another combination for Ultimate. And we have here EH Ultimate. And let's choose the load name as EH. Now to be consistent with the local axis, we have to assign here a factor of -1.6. As per the ACI code, for live load, we have 1.6 scale factor. And click OK. Add the last load combination, which is the WH Ultimate. Click the load name and choose WH and assign here a scale factor of 1.6 and click OK. And we save the different load combination. Now we are ready to assign the load combination, but first let me select the ground level to easily apply the loads. We select the exterior walls and assign shell loads non-uniform. Now we are at the shell load assignment, but we have to select the correct load pattern name, which is, let's have first WH. Let's make sure that the direction is local -3 to be consistent, and also the restrictions is use all values, and for the options we choose replace existing loads. Now as you notice, A and B is 0 because there is no component for the X and Y. Now we're going to supply C and D values according to our computation in the pressure diagram. So let's go back on our pressure diagram. As you notice, the value of C is -9.821 and D is 35.32. So we will supply these values. Forget about -6 and 27.6. These are the values that I have applied earlier. So -9.81 and 35.32. When you're done, click OK. Select Get Previous Selection to be able to select the previous selected walls, and then apply or assign shell loads non-uniform and choose EH. Again, we will retain the direction as local -3 to be consistent. And let's go to the pressure diagram. The value of C and D is -6 and 27.6. So we will supply these values here. This is -6 and this is 27.6. 27.6 positive. When we are done, click OK. Now that we already applied the different values, I have to explain that why I did not apply loads at the interior wall. Well, because the compartment is divided into two equal parts, so the forces or the pressure will be counteracted by each other, and eventually that will boil down to 0. Now we have to view it in a 3D model so that we'll have a better look of our model, and at the same time to be able to figure it out the result of our analysis. Click this icon button here and it will run the analysis. After we run the analysis, you will find out the deformed shape, but we are not after that. Click this icon button here, which will display the shell forces stresses. If we want to find out the maximum service moment, just click the combination that you want to show. Let's say, for example, EH service, and choose M11, display deformed shape, and click apply. If you notice, the wall is being pushed inward, meaning to say that our assumption for the EH or the earth pressure, which will push the wall inward, is correct. If you notice, the maximum moment is almost at the middle. If you click this area diagram here, right click and put your cursor inside, you will find out that the maximum moment is almost -13 kilonewton meter. Now if you want to check some other locations, say for example at this edge, just right click and put your cursor, it's -12, so it's almost the same. If you choose M22 and click apply, you will find out that the maximum moment is at the base, which has a value of -24, or let us say -25 kilonewton meter. So that's for the load combination EH service. What about for the load combination WH service? Let's choose M11 first, or M11. Now the maximum moment is at the center. And if you notice, for the load combination WH, which is the water pressure, it's pushing the wall outward, meaning to say that our assumption is correct. If you click your cursor here, or if you put your cursor here, you will find out that the maximum moment is almost 12 or 13 kilonewton meter. Now, if you want to know also some other locations at the edge, you right click and put your cursor inside, and you will find out that the maximum moment is approximately the same as +13 kilonewton meter. Let's choose M22 direction. Now for M22 direction, the maximum moment, I guess, is at the base of the water tank. Let's put our cursor here and we will find out. And we find out that the maximum moment is 25 kilonewton meter. Or 27 kilonewton meter here. You can also find your maximum moments here. So it's on other locations, maybe at the other side. But this is almost symmetrical, so they should have the same moment. So it's here, 27 kilonewton meter. Yeah, it's there, 27 kilonewton meter. Now we are done showing the different combinations for service. Now we want to show also the ultimate combination. But before that, I would like to clarify that it is not always the ultimate combination which will govern the design. Sometimes we need to check both the service moments for the crack width analysis and at the same time for the ultimate combination. Let's go for the ultimate combination. Let's have EH ultimate. As you notice, for the EH ultimate, it's pushing the wall inward, meaning to say that our assumption is correct. And if we want to know the maximum moment, it's almost at the bottom for M22. If you click this area diagram here, you will find out that the maximum moment is almost negative 41 kilonewton meter. If you choose M11, you will find out that the maximum moment is at the middle. If you click this area diagram and put your cursor here, you'll find out negative 21 kilonewton meter. And if you want to check some other locations at the edge, just right click and it will give you almost the same as negative 20 kilonewton meter. So that's for the EH ultimate. What about for the WH ultimate, or for the water pressure? Click apply and you will find out that the maximum ultimate moment is at the middle. Right click the area diagram and put your cursor inside. You will find out positive 20 kilonewton meter. Also for the edge, right click and put your cursor here. You will find positive 21 kilonewton meter. For other directions, M22, click apply and you will find out that the maximum moment is almost at the base of the tank, which will give a maximum moment of, you can find out also here, the maximum of 45 kilonewton meter, probably in other locations, but at the base of the water tank and almost at the middle of each compartment. So those are the different values of service moments and ultimate moments. Now that I have shown you the different moments, I give you the task to input these values in your spreadsheets for crack width analysis using ACI code, so that you will compare which one will govern. Is it the crack width analysis or the ultimate analysis? Whatever governs, what's important is that you choose the worst case scenario. Thank you for listening on this simple presentation on how to use shell area non-uniform pressure using Etabs. If you have further questions, corrections, or violent reactions, you can comment down below and I will be happy to read and respond to your comments.